In today's lesson on 10.3, the theorem I want you to focus on is the perpendicular chord bisector theorem. It's the second one in this section and it's labeled with number 10.7. We learned in the first section of this chapter that a chord is a line segment with two endpoints that are on the circle, so contained entirely in the interior of the circle. Now this perpendicular chord bisector theorem tells me that if I have a diameter, your book says diameter, this can also be a radius. So either a diameter or a radius that forms a perpendicular relationship, a 90-degree angle, with a chord in a circle, that means that the chord gets bisected. It gets cut into two congruent components, two halves. So we want to apply this to a series of problems I've given you, and I've recreated two of them here on my whiteboard. So let's take a look at number 5. We're solving for x. Now, if you notice, x is a radius of this circle. We have a measure 12.6 and we have a measure 7.3. We also have a right angle. So from the center, going at a 5 or 6 o'clock direction, we have a radius facing south, and the intersection that forms a right angle there tells me that I have two congruent segments here that are both going to be 12.6. So the way I would set this up is I would use the Pythagorean theorem. We have two right triangles that are evident now in our circle here. So x is going to be the c value. It has to be the hypotenuse being opposite from that right angle. So the way I would set this problem up is I would do 7.3 squared plus 12.6 squared equals x squared. We did plenty of Pythagorean theorem problems in chapter 9, so I think you all could solve from there. That one's pretty straightforward. Let's take a look at one more, number 9, that's a little bit more challenging. So x is this segment from this position right here to the edge of the circle. Not exactly a common looking segment here. Something I want to note about the CUDA software is that 8.1 is going to be this half of the chord over here. 18.4, when that's labeled right next to the center of the circle like this, that is indicating a length for a diameter. So right away, when you see a measurement given right next to a center of the circle like this, I would split this diameter into two radii of 9.2. Just cut it in half to get the measure of your radius. So if we divide by 2, we get 9.2. A 9.2 over here. How can I use this to work towards getting x? Well, based off the theorem I learned in this lesson, I have another measure of 8.1. Since I know that there was a right angle in the problem here given, that is what we need for the theorem. So since there's a right angle there, I forgot to include that, forgive me, we have two congruent components of the chord right there. And so I know now that I have an 8.1 up here. So I can't quite get x yet, but I can get this tiny measure, which will allow me to solve for x. So I'm going to solve for, let's create another variable. Let's create y. I would set up with Pythagorean theorem, and I'm going to go y squared, that's a leg. The other leg is 8.1. And that's going to equal 9.2 squared. Let's do this one. .1 squared is 65.61. And that equals 84.64. So I'll subtract 65.61 from both sides. And I'm going to take a square root on both sides to solve for y. So the y value is going to round to 4.4, just round it to a tenth. So if this y value is 4.4, how can I possibly get x? Well, it's a strange segment, we said x, but it's part of another radius. Always be on the lookout for radii in these problems. So we have a radius of 9.2 right here. That tells me that this radius also has to be 9.2. Every single radius in the same circle is going to have the same measure. So the way to solve for x is to take your measure 9.2, subtract the segment we just found, 4.4, that's going to equal your x. So in this problem, we find that to be 4.8.